papers in his scientific records. He published many papers in top journals, including the Journal of ACM, as well as many papers in most important conferences in computer science, including famous Fox, Soda Stock, and POTSI. Translated into Polish realities and situations, it means 200 points for publishing even a single paper in such a very selective conference. Moreover, Darek has been a program committee member of the principles of distributed computing, its POTSI conference for many years, and he was also a general chair of this conference in 2012. I think that's all. I had a pleasure to cooperate with Darek for several years. We have even some joint PhD students already completed, and yes, I hope to continue the cooperation with him. So thank you very much.
Thank you, Marek, for this nice introduction. Thanks for the invitation. So this presentation is kind of suited to the interest of your group. I mean, this is probably the closest I am doing regarding scientific modeling and so on. I'm generally interested in algorithms. I have been for nearly 30 years interested in algorithms, and in particular distributed algorithms, communication algorithms, and so on. But after reaching some certain age, you know, I don't have to prove anything more. I just can do whatever I want. So I just decided to broaden my interests, and I looked into other sciences and started thinking how algorithms may become helpful to other sciences. And I have several episodes to work with biologists, I mean on real biology problems. We publish in either biocomputing conferences or biological conferences or journals. So this is one of the topics, and it is focused on algorithmic models of species migrations and their modifications. And it was done when I was in Liverpool with the Department of Biology, which is also located there. So my motivation, as I said, is that I'm aware that there are several approaches to modeling and solving problems in sciences. And most of the modelings are kind of applied math techniques or physics techniques. And once computers come into play, also several computing toolboxes were developed for numerical computation, optimization, and so on. And this modeling is quite developed. There are several pros, but one of the main from my perspective is that it's reasonably easy to incorporate many parameters to the models. We can create multidimensional spaces and so on. But from my perspective, when I was talking to, biologists, I saw several drawbacks of classical approach. So first of all, it's not that easy to put some subtle dependencies between parameters into mathematical formulas or simple simulation programs. Next, usually when I was talking to people and okay, we identified some problems, they already had at hand some numerical tool or optimization tool and said, okay, so see, we can solve this problem using this tool. And it usually happened that they had some solution, but then after I looked carefully, I find an algorithm that produced much better solution. So if you tailor your algorithm to specific problem, specific model, you can very often find much faster and much accurate solution. At least this is my experience on 3 projects that I already did with biologists. There is some kind of limited control of the accuracy because everything is a stochastic process. So you really have to kind of trust that your process converges and you can stop and you can do some statistics from it. And the most important feature that it's with these modelings is not that easy to manipulate the data. So for instance, if you have, I mean, I will show you later that, for instance, if we would like to change environment to improve something in the process of migration, then it's quite easy to do it once you have algorithmic model for the problem. But if you have some other models, it might be difficult. But I will discuss it a little bit later. So my general approach when I work with other people, also recently with social sciences people, psychologists as well, is first to think about potential algorithms that may solve problems. Because if we come up with a great problem, great description, but I mean, you don't see really good algorithms for this. You may get some solution using classical tools, but they may not be the best possible. And maybe you have to twist the model a little bit to find a better model, but allowing much suitable algorithms. And by the way, if you have any question during my talk, please feel free to ask. Okay, so let's go to more details. So essentially, ecologists with whom I worked were interested in facilitating adaptation of species. And this adaptation means that they are enabled to shift their locations if something wrong happens. So it was important to analyze the speed of invasion from one place to the other. So they analyzed, for instance, some kind of corridors in existing environments or some stepping stones through which the species may jump from one location to the other location. Everything just to help species to invade from one location to the other. Of course, you can imagine the opposite problem, that you have some species, invasive species that you don't want to invade, right? So then you would do everything to slow down rather than to increase the speed of migration. So there are two like angles of the same problem, but unfortunately, these angles are not very symmetric, as I will show you later on. Well, there are a couple of challenges here. So first is that computing invasion time for some real landscape takes time and resources. Then if you want to upgrade the landscape, to modify it, then you have to run the simulations, for instance, again, or twist the model again. And this is computationally expensive because you have to repeat the simulations for the slightly changed environment. And this holds even for moderately sized landscapes. So if you have a big landscape or a very detailed scale of the landscape with lot of patches to consider, then this problem is really hard. So I mean, the groups that we worked with, so there was several consortium of various institutions and universities that tried to develop some good strategies and software to manipulate landscape, to improve the invasions of species. They really had hard times in computing something reasonable. So my goals were of twofold. First was just to look at the model and try to compute the invasion time as quickly as possible, taking as small resources as possible. But the more important was to come up with some algorithms. So from the very beginning, we assumed that this model has to admit nice algorithms, so that later on we could easily change the model, change the parameters of the model in some sense, and argue about the invasion time after we change the parameters without repeating very costly computations. So we worked on landscapes taken from United Kingdom maps. Here you can see kind of simplified maps with only 4 scales of landscape quality. So this map is essentially a landscape which is patched into some small territories. I think it's mile per mile territory. Each pixel corresponds to 1 mile per mile, but there are also more detailed maps. There are several parameters which are measured, but biologists can say, okay, for this species, we are interested in this and those parameters, and let's do kind of a scale like 4 levels of the scale or something like that. So this is kind of a simplified approach that could be used. And here is an example. We took some landscape which spans from the west are the mountains in Wales, and towards the east coast of United Kingdom. By the way, Liverpool is also part of this map. We assume that we have some source. For the purpose of simulations, we assume that the mountains in Wales are the source patches, so there are some species that live there, and the target is to migrate to the east coast of United Kingdom. And this migration is using some population model, which essentially studies the process of populating more and more patches until reaching the target patches on the right hand side. And we are interested in the number of steps of this partial population process to reach the target from the source. Here are more details again. So
Sorry,
we
can I ask a
represented.
question?
Sure.
Maybe it will clarify it in a minute, but so you consider the population as a unit, or it consists of many individuals?
In this model, we considered as binary approach. So either patch is populated or not populated. But we also plan to work on some extensions like partial population, some diminishing of the population at some point at the patch, or even there are some models in which it's allowed inside a single patch to consider growth of population. So it starts from a very small one, and then it grows. Of course, if the population grows, then the probability of jumping to other patches nearby is also increasing.
Okay,
but there are formulas.
Okay, but it's not that it consists of many individuals that interact somehow with each other. It's just the population that's like diffuse or something.
Yes.
through the landscape. Yes.
Yes. This one is about the independent diffusion through the landscape.
Okay.
And
Thank you.
The problem could be represented by 2 matrices. One matrix on the left-hand side is the landscape quality matrix. A quality of each patch, it could be given by some number between 0 and 1. I showed you this simplified scale on the previous slide, but actually we can consider more continuous scale as well. And on the right-hand side, we have a matrix of the actual population status. So the patches with 1 correspond to those patches which are populated. Patches with zeros correspond to those which are not populated. And the goal is to populate more and more patches in order to reach the target. And we also consider different variants, and it happened that this model was good for all these variants. So essentially there are variants like one variant is to reach any target patch. The second variant was to reach a majority of patches in the target. And the third variant was to reach all the patches in the target. Of course, the invasion times for all these 3 variants differ, but the approach produced similarly good results. I mean, similarly accurate and similarly fast results for all these 3 versions. So I will not focus on differentiating between them. Okay, so here is a snapshot what may happen during the computation. So we might have some partially occupied landscape on the left-hand side, and then we do one step of population, and we get another landscape 0, 0, 1 landscape. This is in this setting we assume that it's monotonic, so we can never change 1 back to 0. We only could change 0 to 1, so we don't have dying implemented in the population. So this one step of population happens in the following way, that for each 2 patches in which the first one, patch V, is populated, the patch U is not populated, we compute the probability of population, which is given by this formula, which is kind of well used by biologists. So we didn't invent it, we just got this formula from the biological papers. Essentially, it has 3 major parameters. So Q of patch V is the quality of patch V. So this is the patch in which is populated, the first one. So in some sense, in this, how strong is the population there? If the quality is high, it means that the population could develop fully and has much more power to invade other patches, right? And then there is exponential formula which depends on the distance between the 2 patches, the populated one and the one that we are considering, and parameter alpha, which is called dispersal coefficient, and it depends on specific species. So depending on which species we consider, we may have this parameter different. So you can see that usually these probabilities are not so big, but we consider these probabilities for each pair of patches in which one of them is populated, the other one is not populated. And we toss a coin with this probability, and if it's positive, we populate patch U. If it's not positive, if the result of tossing the coin is not positive, then we don't populate patch U. Of course, patch U may be populated from different patches V, right? Because we are tossing a coin several times. For each populated patch V, we toss a coin whether it populates patch U. So more or less, it's a quadratic number of random variables that is involved in a single population step, right? Okay, so different groups consider different approaches. As I said, some groups considered models based on differential equations and methods called forced field methods, which I'm not very familiar with, but I'm just quoting that there are such approaches in this particular area. Most of the groups use simulations using, well, these are Markov processes actually, but essentially what they do, they simulate each step and they repeat several times the simulations, do some statistics and so on, then they modify the landscape and repeat the process, right? So the disadvantages of both of these 2 methods is that they don't scale well, and they don't scale well in the size of the landscape, but also with the number of changes that we want to do in the landscape. So it's most of cases it's exponential dependency. So really, we can't really grow a lot. So this also means that we cannot easily manipulate the landscape, because each manipulation may cause us to repeat the whole process. So it's either kind of numerical computations involved or some simulations involved, and we have to repeat it from scratch. So the first paper that we got with my PhD student and my colleague Prudence Wong from the department and Jane Hodgson from biologists, we published in ICCBB conference, and then we had 2 follow-up papers in this area. At some point we stopped because I moved to Augusta University, but there are still several very nice variations that could be considered. So our first approach was to find analogy with some simpler model that was already tractable by some algorithms and some nice analysis. So I was working a couple of years ago with so-called push-pull protocols, which are protocols that are used to spread rumors in networks modeled by graphs. So these protocols essentially use two operations. So we have a given graph, and each node independently in each step does a push or pull operation depending whether it's informed already or uninformed. Informed means that the message, it got a message at some point. Uninformed means that it never got the message before. So if someone has a message, so is informed, then it selects randomly one of its neighbors and pushes this message to that neighbor. So that neighbor receives this message and becomes informed. If, however, the initial node is uninformed, then it does an opposite operation, so pulls. It chooses randomly its neighbor and asks if the neighbor has the source message. If it does, then it pulls this message. If it doesn't, then of course, nothing changes in the system. So this is kind of a very nice area of research in computer science as well. There are some mathematical analysis, estimates of time of propagation of the message in the graph. There are, however, a couple of differences. So our biological migration model is a little bit more complex. Two main differences are that push and pull operations are studied in very simple unweighted graphs, and they were analyzed in such graphs. And these analyses were only asymptotic, so up to some constant factors. And also push-pull procedures in the rumor spreading protocols work at vertices. But we actually, in our model, we work with edges. So for each pair of patches, we check whether patch V invades patch U. Right? So this random process is at edges, not at nodes. Okay, but there are also a lot of similarities. So these similarities, by analyzing them, we came up with some specific measurements in our to form our algorithmic model for migrations. So first of all, we said, okay, so let's model our landscape as a network. I think I have a picture of this network somewhere here. So it's a very dense network because in theory, there are possibilities to populate even faraway patches from some other faraway patches, but of course the probabilities are very small. But it depends on the accuracy that we can get. This network could be dense. We add two artificial nodes to this network in order to make it algorithmic. So some artificial source node, which is connected to all the source patches, and the target node, which is connected to all target patches. And there are these connections that with weighted connections that correspond to the probability of evading from one patch to the other patch. Of course, this could be also reverse invasion. It doesn't matter, it's natural, because for instance, if you imagine an obstacle on the way, sometimes it's better to invade backwards and find some detour in order to reach the target. Let me get back to the previous slide. So based on some analysis of similarities between push and pull rumor spreading model in graphs and our migration model, we came up with some measurements. So one measurement is, we call it beta with parameters, with parameter k. Here, capital N stands for this network that I just showed you a minute ago. And this parameter beta is essentially, if you consider all cuts in this network, in which the initial sites, the source site has exactly k vertices, and the other side has exactly n minus k vertices, where n is the number of all nodes in the graph, then you can sum up all the weights of these edges in this cut, and you take the minimum. So it's essentially kind of minimum weighted, directed k cut in the graph, in this network graph that we define.
It's like,
of course, people considered similar. Yeah,
it's like a maximum flow problem, which is the dual interpretation.
It's so this one is very similar, yes, but then we came up with the second measure, with this gamma measure, that actually measures the sum of the inverses of these beta parameters. And this is unfortunately not the max flow problem, because this is not a linear function of the coefficients beta. It's a convex function, okay? But it's an important observation that although it's not a network flow problem for which there are some polynomial time algorithms, so we could apply them and estimate the invasion time, but at least it's these coefficients beta, which correspond to cuts, are used in some not very complex convex function, which is the sum of the inverses of these parameters beta, where the sum spans from k equal 1 to n minus 1. So this essentially we measure cuts of different balance of sides, right? And we sum up the inverses of the minimum cuts of different balance over the two sizes. Okay, so the similar measure was considered, as I said, in the push-pull protocols, and it gave quite nice estimates for rumor spreading in graphs. And essentially, the theoretical results said that the rumor spreading time is essentially asymptotically, so it's this big O means asymptotically not bigger than the value of function gamma that I just defined on the previous slide, this function. So at least you have some upper bound on the number of... Yep.
Can I interrupt you? Because we are sitting here and we are still thinking about this cutting, and I'm afraid I don't understand it fully because I was never doing this. So could you repeat once again how you do this? How you cut? I mean.
So let's fix a parameter k. Parameter k is between, as you can see in the sum below, it should vary from 1 up to n minus 1, where the small n is the number of all vertices in this network model that I just showed you. Okay, so let's fix this parameter k, and let's consider all the cuts. And by a cut, I mean we partition vertices into two parts. One part containing the source node here. So for instance, we can consider some part here, contains exactly k elements. And of course, there is the remaining part. And then we look at all edges that are directed edges from one part to the other part. Okay, and we sum up their weights, which means in our case, the probabilities. Okay, and then we minimize it over all possible such cuts. The sum of edges here in one cut, we take the minimum such sum over all possible cuts that we can have.
Okay.
So this is like minimal flow between the parts, or something like this?
Yes, between parts in which one part has exactly k elements.
Yeah. And the rest of the system.
Yes.
Okay. Thank you.
So this is something which is quite standard in kind of algorithmic field. It's called network flow algorithms, and there are different variants studied and so on. Some problems are easy. For instance, the classic network flow problem, so computing the maximum flow, which is equivalent to computing to minimum cut in such network. is a problem which has several polynomial time algorithms, but there are also variants which are NP hard to compute. So no polynomial time algorithm is known for such variants of the network flow. And this is kind of related to kind of variant of this problem for the weighted directed graphs, which is not tractable in polynomial time. At least we don't know. It's NP hard problem. So this is because of this gamma function, because this gamma function is not linear. This gamma function is inversely proportional to these coefficients beta. Okay, so I don't have clear intuition why we chose this gamma function here. If I have to explain it to you, I would have to go back to these push-pull protocols and then introduce the whole theory and show you that in these push-pull protocols, this measurement was really good. So it was really good estimate, upper estimate of rumor spreading time in networks.
Can I have one more question? So can we understand this beta k? Like we always choose the most self-contained k element part of the network. By self-contained, I think that if the outflow from this part is minimal, so it might mean that it's the most self-contained thing, because all the flow goes inside.
Inside, yes.
Not all, but the majority of the flow. Something like this.
Yes. This is a good intuition. Yes. Yeah. So as I said, for push-pull protocols, this gamma function was a asymptotically good upper bound. And actually, there are several examples showing that for many classes of graphs, this gamma function is also a lower bound, asymptotic lower bound. So it's a very good estimate for if one wants to compute it, to estimate without like running several experiments on the graphs and so on. This could be done. Unfortunately, gamma function, I didn't find a proof that it's NP hard, but I have a strong suspicion that computing gamma function for complex graphs might be NP hard. So when we translated this gamma function to our migration model, the question was, okay, so how to compute this gamma function if we don't even know how to compute it in a simpler push-pull rumor spreading model. So to do it, we used this intuition that it's actually these beta coefficients correspond to some kind of partial flow. So these self-contained parts, right? So what we said, okay, so maybe we don't know how to compute exactly this gamma function, but let's try to estimate it. So we came up with some kind of recursive formula, which is given here on the slides. So we partitioned landscape into some kind of smaller pieces, like 10 times 10 patches pieces, kind of windows. And then for which window, we computed the number of patches in this window. If you look here in these ratios here, in the denominator, you have logarithm of the number of patches, non-zero patches. So patches which are kind of, because if you have a zero quality patch, it doesn't matter. I mean, it will not propagate further, because if you recall in this probability formula that I was mentioning, in order to populate from V to U, the quality of V must be non-zero, right? So, so here we take this ratio. In the denominator, we put logarithm of the non-zero patches, number of patches in this 10 by 10 window of patches. And in the denominator, we compute the maximum flow from right-hand side, left-hand side of this window to the right-hand side of this window. Okay. And then we recursively compute our invasion time for several windows, and then we compute for the next window and add them. We also have to scale them a little bit by some constant here. And we said, okay, so let's come up with this model and let's evaluate whether there is a constant C in practical experiments that really gives us good, that really makes this model, this formula, good prediction for invasion time, because this, as you can see, this formula computes invasion time on some prefix of the landscape, right? So we take the prefix, we take another one and another part of 10 columns, compute something on this, and add to the invasion time on the prefix. And so we keep adding, and at the end we get invasion time for the whole landscape. This is again the network that I showed you before. So this technique we use, this network we use for this 10 by 10 patches, so we don't use it for the whole network. There are a couple of reasons. We found that we cannot use it for the whole big network. We have to somehow use it for smaller windows and then combine them together window by window. And here is, I can tell you about some results that we got. So we considered several randomly chosen landscapes, but by randomly I mean we found random part of the landscape in UK map. So it's not like randomly generated landscape, it's a real landscape, but the coordinates of this landscape on the map were chosen randomly, right? So we found some random part of landscape of low quality, so the black and blue dominate here, and these are low quality patches. We found some landscape with medium quality, which essentially is a mixture of all fall colors on the map, and some landscapes with high quality patches. And this landscape spread over 300 miles, so they were quite big. The only thing that for the purpose of experiment so far, we use not too high landscapes. So we essentially use the long landscapes, but not very high. So we plan in the future to address also the higher landscapes. The reason, the motivation for using this one was first, let's try the model on slightly smaller landscape. And the second, that actually biologists were interested in something like, okay, try to identify corridors. So try to find out whether these kind of corridors are nicely invading or badly invading. So our first question was whether this model gives us accurate prediction of invasion time. Invasion time is just a number, right? How many invasion steps we need to proceed until reaching the target patches, right? So we can compute it by simulations. So we already had software for this. So we computed for these three types of landscapes, we computed by simulations. And then we run our model. And you can see the ratio between the time computed in simulations and time computed in our model. The higher and this is measured for different width of the landscape, so up to 300 miles. And you can see that actually the longer the landscape, the closer to 1 we are. And so this ratio is really like 5% or sometimes even less than 5% difference for different quality landscapes. And for different invasion coefficients alpha, which as I could recall you, correspond to different types of species, right? So different types of species have different coefficients. And so we tested several, just not to be biased to some specific species. And for all of them, essentially, we get very close to 1 accuracy. Then the second question was, oh, okay, we delivered a new model, entirely different nature than the previous ones. But I mean, how about the computational time? Are our algorithms faster than the simulations or not? We actually run on the same machine, the same environment, both simulations and our algorithm, using the same language and so on. And here are the improvement results. So the simulations, the actual computational time that the machines took when doing simulations and when doing our prediction model. And you can see that this is an exponential scale or logarithmic scale, depending how you look at it. And really it grows here. So really our approach is exponentially faster in terms of computing. And now even in terms of memory that is used, because in our process, we also implemented some process of sparsification of this network. So we essentially get rid of some that we thought are not very important connections in this network. Of course, this was like a methodological approach. It's not like that we arbitrarily removed something, right? We had some kind of algorithm, some criteria to remove it, and we did it. So in this way, we used much less memory, and we were able to save lots of memory. Here the scale is not exponential, here is the linear scale, but still you can see that save on the memory comparing with memory used by simulation algorithms that were designed by biologists is kind of also substantial. So this was about the very basic estimate of invasion time. So our models seem to be very close to the accuracy of the extensive simulations, and exponentially faster and more than linear, less memory using. Okay, but then the second part, just very quickly, because I think we are running out of time. So I think I have only 2 or 3 slides more. So how to improve this landscape to improve invasion time? So to shorten it, to minimize. So the question was like this. You have a given budget, capital B, which is some number. And you have to distribute this capital B budget into small pieces to some patches. So essentially, if you can take some, let's say, some value, let's say 0.01, and put it to some patch, and this way the quality of this patch increases by this value. So we increase the quality of the patches. This way the probabilities increase, and we can reach faster the destination. So how to optimally distribute this budget to minimize as much as possible the invasion time? Of course, this minimization is bounded by the amount of budget that we have, this capital B, but still it's possible. So we use this kind of generalization of linear programming, which cannot be linear programming because, as you recall, our function gamma, the main function used for measurement, was not linear, but inversely proportional to these coefficients beta. So it's convex function. So essentially, it's a minimization of the convex function. I don't have time to go into details, but this is something that corresponds to this function gamma. Here is the budget which we distribute among the patches in the network model. And we say that the newly created network has now qualities which are original qualities. We've added these pieces of budget which are distributed here. And of course, this probability formula has this thing here. And we wrote this kind of program, and it happens that convex minimization of convex programs under some conditions is tractable by polynomial time algorithms. So it's efficient, optimal solution. So we computed such optimal solutions, and here are the results. So we compare it with random allocation and with some heuristic algorithms that are used by biologists in practice. So these heuristics are really used in practice by some societies that advise local governments how to modify the landscapes and so on. And the CP-IMF is our algorithm. So you can see that our algorithm is, in terms of number of rounds, it's much, much smaller than the previous approaches. Yes, I mean the number of rounds for the it's not the computational time, is the number of rounds of population. So it's actually the invasion time that we measured here. So here you can see that, for instance, in some cases, our time is tremendously smaller than after these improvements, that when the budget was distributed randomly or using heuristics already made by biologists. And here is an example. If we start with this original landscape, our algorithm produced some nice amendments, some nice distributions of budget B. And when you put this distribution of B on the top of the initial landscape, you got this newly upgraded landscapes. And you can see that in some sense, without any kind of hints, the algorithm started created some corridors. So this is some magic that came from this approach by network flows combined with some convex function optimization and so on. Magically, the biologists wanted corridors, they have corridors. But we didn't really program corridors. I mean, they came up by themselves. So let me finalize. So this was an example of works for 2D landscapes. We plan to extend it to some some higher landscapes, consider more sophisticated models with not binary populated, non-populated by some other twists. So there are several extensions, and more hopeful, I mean, if you are interested in trying to apply maybe a more algorithmic approach for your problems, I would be happy to discuss details at some point. I mean, I'm available. So thank you for your attention.
Thank you very much. I don't know who who should speak right now, me or Marek, but yeah, thank you. And now it's time for questions. First of all, thank you very much for a very interesting talk, and I learned a lot. Although I don't understand many things still, but I will ask maybe. But maybe other people have some questions.
So I have a question. I don't know whether I understood it correctly, but this network you displayed, it's based on this square lattice of the environment. Yes.
Yes, correctly. On this, the qualities are from here, and the distances are Euclidean distances in this matrix.
Okay, okay. And yeah, because I thought that sometimes you probably can utilize this property of square lattice, but by just cutting paths which are too long or where the flow is very low and they don't contribute to overall flow too much, and maybe this can speed up this process. I don't know, but just that's my question. That
yes, I think that's a very good point, because we actually plan to consider some other manipulations, and this is actually what biologists do, that they create these heuristics in which they look at, for instance, at very long paths that end at some point. So they have some couple of heuristics, but they are really heuristics. They don't have really formal arguments that they should help or something. What we plan to do is to incorporate some other techniques on the top of it, but kind of methodologically. So if we incorporate some other mechanisms, for instance, trimming some paths in this network, then it should have some motivation and some argument that it will be consistent with the rest of the algorithm, right?
Like
it's a very interesting direction.
Like some network measure, and then you just put the threshold and say that, okay, everything above or below, I just cut. Or
yes,
yeah.
And this is, for instance, the approach that we did when we removed some edges from the network. Then we did some pre-processing, we measured some parameters, and then we decided, okay, these edges are not important, so let's remove them.
Also, with sorry for taking this time, but also I have a question regarding this gamma measure. So can this be understood as measure of granularity of the network or this environment?
Some sense, yes. It's also related to the conductance of of networks. So something which is related with Markov processes, but it's not that simple. I mean, that relation is not that simple.
So because if it's larger, then means that the flow that beta is smaller. So the flow between the parts is smaller. So that means that there are some granules for higher gamma, but for lower is rather a smooth structure or something. Yeah, I know that K increases, and this can be the same part, but just increased by some nodes, and then there are some steps. But I don't know. That's my question. That whether it can be understood as the measure of granularity.
Could be, but we didn't have enough time to dig so deeply into the properties of gamma. As I said, we also didn't know whether exactly computing it is NP hard, so whether it's related to some hard problem or not. We suspect it is, because it's, as I said, it's related with conductance of the network, and conductance, computing conductance is.
And have you checked whether it's related to some community detection algorithms, this gamma, or?
No, we didn't.
No, that could be also interesting case, because it seems like really nice network measure to measure network overall, and I don't. Yeah, so that okay. So that was all from my side so far.
Thank you.
Okay, thank you, Piotrek. So I see that you understood much more than me, because I already have a problem with, maybe there are some other questions from people that understood more. Okay, I will have a question. So I don't really understand how you convert this, in fact, square lattice into the network. I understand these probabilities, how you put weights on your network, but I don't understand how you really convert this landscape that is like two-dimensional landscape into. Yeah.
So you take this big landscape and you partition it in a special way into windows 10 by 10. Okay, and for each of these windows, you calculate such a ratio here.
Okay.
This ratio. So it's essentially a logarithm of the number of non-zero patches in this window divided by maximum flow. So how much flow is, what is the maximum flow that you can propagate through this 10 by 10 part from the left to the right. Okay. So actually this network here is created for each of these 10 by 10 pieces that you have in this big matrix.
Okay.
And then once you calculate these parameters for each of these 10 by 10 pieces, you go from left to right and you keep adding these things that you computed. Okay. As I said, there was a problem. There were some methodological issues in that we couldn't create like one big network for the whole matrix. We had to first split them, kind of cover them by some 10 by 10 pieces, and then compute something for each of these pieces. And then going from source to the target, we keep adding what we computed, all these ratios for these parts.
Okay, thank you. Some other questions, maybe? I don't see more questions. I have one question, but it's not related really to like, it's not really technical questions, and I don't know if you can answer, because it's not like the question for computer scientists probably, but I'm really curious, how does biologists measure the quality of the patch? I mean, because they have to translate in the end, they needed really to some forecasting of real environment. So And of course, the quality of patches includes many things, like also the other species that are living there, and like some predators, for example, or something. So how do they really measure in reality the quality of patch?
So in these applications that that we dealt with, so in UK there are not many predators actually. So so they focus on plants and stuff like that. So they measure what type, some major types of plants, and for instance, what is the percentage of forest and what type of forest on the patch, what is the percentage of water, whether this is a city, for instance, if it's like a concrete thing, and then of course it's nearly zero, right? I mean, the landscape quality. So they have several parameters, and then they have some formulas to combine them. And to be honest, I don't know much details, but if someone wants to have more detailed simulations, it is possible because the real data have many dimensions regarding the percentage of concrete, the percentage of water, the percentage of forest, and so on, and even what type of forest. So,
okay, but in the end, this model does not. I mean, the transition probability depend only on the quality of the patch I'm presently on. So it does not contain the quality of patch I'm moving to.
Yes. So we consider also the other variants, and they seem to be quite similar. So essentially, we could consider the other patch, but we said, and biologists agreed that actually the quality is important for the species to multiply to reach a certain level to jump to other patches. So this multiplication factor at the original patch is the most important thing. So this is why they propose to just keep on the quality of one patch, not both patches. But if they said, if we are going to consider both, there likely be like a multiplication of both qualities, or a square root of the multiplication of both qualities, something like that.
Yeah. Okay. Of course, the most interesting thing is that you can really increase the speed of everything, and I'm really curious if it could be used also, maybe just like, because we have this problem, we are investigating phase transitions, so we usually have this problem that we have something which is called critical slowing down near the critical points, and I'm really curious if maybe this kind of approach could be used also for this type of problems. Do you know something about this or not really?
I don't know much. I mean, when doing my master thesis, like nearly 30 years ago, I was dealing with kind of like Ising model by Bayesian networks and so on. So I consider similar things, but it was a long time ago. Probably the best way would be if you have some kind of a talk that you think in this area on your seminar, that you think that I could understand and see where the problem lies. Then I could try to attend, and then I could give you my opinion whether it's a potential way to collaborate and do something better.
Okay, yeah, for sure we will write you and we will comment. Yeah. Okay, so I don't see more questions.
Well, actually, I have a question.
Okay.
Let me get a bit closer. You said you are considering these patches of 10 by 10. Does it, I mean, this is kind of an ad hoc assumption, why 10 by 10? Does it make a difference in the way that the networks are structured if you change the size, let's say to 5 by 5 or 20 by 20?
We tried different sizes, and for the length of 300, by doing simulations, that 10 by 10 were the fastest and giving sufficient accuracy. But it could be bigger, and probably if we consider bigger landscapes, it would probably be even better to have them scaled up a little bit. But we didn't study actually how this, I mean, we didn't study more rigorously how the size of these small windows should correspond to the size of the whole landscape? This is an interesting question.
Yeah, I mean, my question was also in the direction. I mean, was the network the network you obtain from these patches of different size were there any differences with, I mean, qualitative differences in the networks you obtain?
Not much, because we used polynomial time algorithms to deal with those networks. So even if we increase twice the size, I mean the height and the width, the network grows like maybe just few times. So from perspective of polynomial time algorithm, it's not a big issue. Of course, we will have growth in time, but it won't be exponential as if we used simulations, for instance. So it's still tractable. I mean.
Okay. One more question. I mean, I understand that I mean, a chessboard, a square lattice is convenient, but of course, in terms of kind of the movement in different directions, a hexagonal grid would be probably better to model the potential movement in all directions. Are there any models that actually utilize hexagonal matrices, or is it just square lattices that are used?
From our perspective, should not be a big difference. It's just the distances will be calculated, and the shape of the network may be a little bit different. But at that moment, there were no maps that were based on hexagonals in this respect. So they were really like squared maps of UK, and we also had maps from, I think, Sumatra and Borneo or something, but all of them were squared, so we were bounded by this.
Okay, thanks.
Okay, and now I can stop recording. That's